Okay, good morning. So I want to teach you the new rule, the complement rule. But before that, if you remember last time, we solved that problem, and I really wrote a code in Matematik, and I confirmed that the number I got is really correct. I don't know how many of you have already done that. Okay, there are two more examples. I want to go through them, and then I start teaching this short lesson, and then I give you time if you want to review things yourself. Okay, but instead of me starting solving these problems, I want to give you a little bit of time to think about example number 7 and example number 8. Then I will start solving them for you, okay? So let me see if I haven't done. So example 7, how many 2 by 3 rectangles are there in a 5 by 6 checkerboard? So if you remember, we solved something similar about how many squares you can fit in. And then now that we know the sum rule as well, I can ask you about the rectangles. So how many 2 by 3 rectangles are there in a 5 by 6 checkerboard? And that's, by the way, interesting question. How many squares are there in a standard chessboard, 8 by 8? So we want to see how many, in total, how many squares we can count in a checkerboard, a standard board. Okay, so I will wait for you. Okay, any ideas? Or at least a strategy, for example. Of course, I have been a little bit careless when writing the question, because 5 by 6, usually 5 is the number of rows and 6 is the number of columns. And then I have written 2 by 3. This gives you this wrong impression that this should be a horizontal one with 2 rows. But I just fixed that in the beginning of the problem. So I want to consider all rectangles with dimensions 2 and 3. So it doesn't matter if it's a horizontal one or is a vertical one. Okay. Okay, so I actually told you the secret to the problem. Yeah, so you need to count the horizontal rectangles that you can fit here with dimensions 2 and 3. This is one time. And then you have to count the other one, which are vertical, and then add them up because of the sum rule. Yes. And the reason is that we can use the sum rule is that there is no overlap between them. If my rectangle is horizontal, it cannot be simultaneously vertical as well. So there is no overlap between them if I start counting them. Okay, so what should we do here? So first of all, let us understand how many horizontal. So let me write the number of horizontal 2 rectangles with dimensions 2 and 3. And then I can also have the same thing. So the number of vertical, and then you continue like this. Rectangles with dimensions 2 and 3. So you know that if I count the number to be n1, and if I calculate this one to be n2, because there is no overlap between these two group of rectangles, then it means that I can actually add them up. Okay, but now tell me, how can I count these numbers? Of course, I have given the dimensions of this rectangle not that very big, but if the dimension of this one grows, then you need to have a good strategy in calculating the number of demanded rectangles. So how should I do that? I would prefer to draw one of them as a representative. So I want to have a rectangle of dimensions 2 and 3, and to be horizontal. I hope that you agree this is one representative of those rectangles. Okay, but for counting these, you have a little bit of experience of something like this before. So how can I know the number of these rectangles? And you have also enough experience. Sometimes when you want to use the sum rule for each case, you need to use the product rule. Yes? So if I want to use product rule, I need a task that can be accomplished in 2 stages. So here, if I want to see, do you agree with me, if one way of giving you to specify this rectangle is really to draw that, but there is also an indirect way, yes? If I give you this point and that point, and if I give you this point and that point, then you immediately can draw the blue rectangle yourself. So what matters is to give these 2 points and these 2 points, yes? So I can break down my task of drawing a blue rectangle to 2 stages. Picking up 2 points with distance 2 between them, because I want to have the width to be 2, and on the vertical axis, and I want to choose 2 points with distance 3 on the horizontal axis. Do you agree? So this task is in one-to-one correspondence with choosing these points and these points. Okay, in how many ways I can choose these points? So I can choose my finger with width 2, yeah? So this is one choice, 2, 3, and 4. So I can choose these points with distance 2 in 4 ways, yeah? So this can be done in 4 ways. So if I want to answer now in 1, the first stage can be done in 4 ways. And now I want to do this one. I want to choose these 2 points, but the distance should be 3. So one possible choice is these 2 points. This is one possibility, the second one, and the third one, and the fourth one. So again, I have 4 choices, yes? So I multiply it by 4, so it becomes 16. So I will definitely have 16 horizontal rectangles with dimensions 2 and 3. Is that clear? Okay, so let us test this idea here again. So if I want to do that, let me also draw a vertical one here with dimensions 2 and 3. So for example, let me draw it from here. This is also one type of vertical rectangle with the same dimensions. And then you see that for the same reason, this time I need to give you these 2 points. I also need to give you these 2 points. Yes? But this time the distance on the vertical axis should be 3, and the distance on the horizontal axis should be 2. Yes? So how many times I can choose these pairs? So the distance should be 3. So that's one choice, the second choice, and the third choice. So I have only 3 choices, yes? And then this time I want to have the distance 2. So I can start from here, 2 is 1, 2, 3, and 4, and 5. Yes? So then I will have 5. So the answer becomes 15. But the question mark is actually the sum of these 2 based on the sum rule. Yes? So it is n1 plus n2, and that is exactly 16 plus 15. It becomes 31. So there are 31 of these types of rectangles in total. Yes? Is that clear? Okay, that idea also works for the second example, of course. Then what is your opinion about, I want to count all possible squares in an 8 by 8 standard checkerboard, yes? So for example, how many squares of dimension 1 are there? Yes, 64, yes? But then I need to count dimension 2. For example, a dimension 2 means a 2 by 2 square. Then I will count the number of 3 by 3 squares, and then 4 by 4 squares. And consider all of them. And the biggest one is 8 by 8. Of course, 8 by 8 is clear. How many of them are there? It's just, okay, but what is the strategy? Yes?
Well, I started with 1 by 1 and 2 by 2 and all the way to 8.
Exactly, that's the way how it works. So, and then what do you do with the numbers that you get? You add them up because there is no overlap between them. If you have a square which is 1 by 1, it is definitely not simultaneously a 2 by 2. And if it is 2 by 2, it is not simultaneously 7 by 7. So these different parts do not have any overlap. So if I count each part and then add them up, I will get the final answer. Okay, and then you realize what is happening here. So what is that? I would say that, okay, how many of them are one by, let me start with one by one. Or let me start with, yes, one by one is good. So how many, again, the strategy is clear. If I want to have a one by one square, it translates itself to choosing these 2 points and these 2 points, yes? So I need to ask myself how many ways I can choose these 2 points on the vertical axis and how many ways I can choose these 2 points. For the case of one by one squares, the dimension should be 1, so the distance between these two is 1, the distance between these two is 1. So how many ways I can choose these? One choice, second, third, fourth, fifth, and then how many? 8, yes? So I have 8 choices for these points. And then again, I will have 8 choices for these points. So that's exactly what you know. So it's 8 by 8. And then how many of them are 2 by 2? So let me just try to convince you because I just want you to understand what's going on. So if I have a 2 by 2 square, any one of them that you want to pick, a 2 by 2 square corresponds to 2 points on the vertical axis with distance 2 between them, and then corresponds to 2 points on the horizontal axis with distance 2 between them. And how many of them I can fit? You can see that I can have 1 choice, 2, 3, 4, 5, 6, and 7. So I have 7 choices. So this means that plus I have 7 choices times 7 choices for each case. And then you can see that if I have 3 by 3 squares, it will affect the number 7 by just 1. It becomes 6 by 6, yes? So then hopefully you understand what is going on. And then you continue 2 by 2 plus 1 by 1, that is it. And that is the sum of the squares. Because that's interesting. So it becomes 1 squared, let me write it the other way around. It becomes 1 squared, 2 squared, up to 6 squared, 7 squared, and 8 squared. So that's the total number of squares that you can imagine in a standard checkerboard. And I don't know, when we were dealing with mathematical induction, I found the formula for this, if you remember. That's also a famous formula. So this formula we learned when we were dealing with actually arithmetic progression. We were also able to prove it using mathematical induction. But for the mathematical induction part, I am sure that I also solved this problem for you, that we prove this is equal to n times n plus 1 times 2n plus 1 divided by 6. Of course, for this case, it is not that hard. You can just calculate these numbers and add them up. But here, let us use the formula. So this becomes 8, because n in this case is 8, times the next number, which is 9, times 8 times 2 plus 1, which is 17, and then divided by 6. So 6 by 3, 2 times, 9 by 3, 3 times, 2 by 2, 1 times, 8 by 2, 4 times. Yes? So that becomes 51, and then this becomes 204. So the answer is 204, yes? So there are 204 squares in total that we can imagine in this one. Okay, so that's also an exercise I want to know about. Okay, now the sum rule is finished. Of course, we can have a lot of very interesting problems. If we have time, I will bring some of them and work them together, because there is no way that I can teach you. You know, any problem is different from the other problem. There is no guarantee if you solve one problem, you can solve the next one. And that's the nature of this great mathematics, especially in the topic of combinatorics. Okay, so what we do, I want to go to the next rule. Oops, where is it? Just wait. Okay, so the complement rule or the complement principle. I think the name suggests itself, yeah? So this is this. The number of desired possibilities is equal to the total number of possibilities minus the number of undesired possibilities. Yeah, so that's very clear. So if you are interested, sometimes this rule will help you to count things easier and faster. Okay, I will try to give you some ideas how it works. But this is clear, yes? So if I want to draw, it's like a complement in the set theory, yes? So actually, essentially, this can be expressed in the language of the set theory, yes? So if I have, this is my universal set, assume that this is all possibilities that I have, and then this is what I want to count for some reason I am only interested in these items, as a set, let me call it set, and you know what is outside in set theory, it is called a complement. Yes? This tells you that if you want to know the cardinality of the complement of a set, if the set is finite and if the universal set is finite, what you do, you write the cardinality of the universal set, in this case means all possibilities, minus, so let me write it the other way around, minus the cardinality of the A complement. So that is exactly the complement rule. If I am interested in the number of items inside A, what can I do? I can count the number of items in this big rectangle, the universal set. I can count how many items are outside A and then subtract them. It's very clear. So that is, I would call it complement principle again. Okay, but sometimes it really helps. Okay? So for example, consider the following problem. Using only 0, 1, 2, 3, and 4 as digits, how many 3-digit numbers with distinct digits can be written? Okay? This is not something that you really need this rule to solve it, yes? And that is the reason that I have asked you using the product rule, using the product and complement rules, okay? Because sometimes it is easier for us to think in this new setup. I mean, I have a lot of experience. So when you want to solve a problem, I don't know, suddenly this comes to mind. Let us count the whole possibilities and let us remove the ones that we don't want to. Okay, of course, not for this simple problem. For this simple problem, we can use it immediately. I would recommend you to do it in that way. The reason that I want you to solve it in 2 different ways, because I want you to compare. Okay? Okay, so let us solve this problem. The digits are 0, 1, 2, 3, 4, and I want to write a 3-digit number with distinct digits. Okay? So this you can help me to solve it. Yes, how should I solve that? So the digits that I have are 0, 1, 2, and 3, 4. Yes? So how many 3-digit numbers I can write with them without repeating any digits? So you know that I have a 3-stage task. This is a very simple problem. So which one do you prefer to choose as the stage 1, as a rule of thumb? Yes? The left one, yes? Because here I have a little bit of limitation. I cannot put 0 in. So I would call it a stage 1, and it doesn't matter which one probably I call stage 2 and a stage 3. How many options are available here? I can choose whatever I like except 0, so there are 4 options. But because I am not allowed to repeat any digit, so this means that I have used one of these digits. I don't know which one. Let us assume that I used 4. But for stage 2, how many are left now? 4 again, because this time, even though I cannot use 4, but I can use the 0. So it's 4. And then what is your guess for the next one? 3. So the answer is just 48. That's extremely simple problem. That's not the point of this exercise. I want you to solve this problem now using the complement rule. So in the complement rule, for example, we can imagine that I just generate all possible arrangements, even if 0 is in the beginning. Yes? Of course, this is the total possibilities, but those that start with a 0 is not desired. So I take them off. Yes? In this problem, I am not making the solution easier. I am making it harder, but the point is to learn these ideas. Yes? So if I want to do that, what I say to myself, I would say that, okay, let me see how many ways of arrangements I have, regardless of if it starts with a 0 or not. Or you can say how many codes I can write with these numbers without any repeated digits. So then I would say stage 1, stage 2, stage 3 as before. How many ways I can fill up this if I do not have any restrictions at all? 1, 2, 3, 4, 5. Yes. But one of them is not dropped. So how many of them left? 4. And then 2 of them are so far dropped, so 3. So if I multiply them, it becomes 60. Okay, so 60 is the total number of arrangements, regardless if it starts with a 0 or not. But I don't want this to start with a 0. So if I can count how many of them start with 0, then I take them off, and what is left for me is done. So if I want, so this is the total number of codes, yes? Something like this. Okay, how many of them start with a 0 on the left? Okay, so I need to count these, which are not desired. I need to take them off. So how many options are? So I am here counting those codes that start with a 0. So then how many options I have for S1? Just 1. I put 0 there. So the number of ways I fill it up is 1. I am choosing 0 to be here. So I have 1 option. And then how many options are left here?
4.
4. And how many options are left here?
3.
3. And if I ask you how many of them are there? 12. If I ask you what is 12, you will tell me 12 codes start with a 0. How many codes I have in total? I have 60. But I want a 3-digit number, so I need to take this off from that one. So this is the total number of codes starting with a 0. With 0, okay? So, and then the question mark that I am interested in is 60 minus 12, and as you see, I really get the same answer, 48. Of course, in this problem, as I told you, I didn't make the problem simpler to solve, even I made it unnecessarily longer. I just want you to understand in this simple set of what I mean. Yes, is that clear now? But hopefully, the other examples, if you think in the complement way, either it is more natural for human brains or whatever, or sometimes it is really easier to work it in that way. Okay, so let us now go, and I want to wait for you, okay? So you see here, example 2 is a good example, I would say. It's very simple, but it will illuminate why this is useful. How many 3-digit numbers are there so that each contains this word, at least 1-5? Okay? I want to solve this problem in 2 ways again. One, not using the complement rule, and another time using the complement rule. It is extremely important to go back and forth between these methods to learn these things yourself better. I want to wait for you a little bit. So how many 3-digit numbers are there so that each contains at least 1-5? Okay. So let us solve example 2 first, but without using the complement rule. You really don't need the complement rule because you can use the product rule and the sum rule to solve that problem, but then you will see that using the complement rule makes it easier. So I am looking for 3-digit numbers which contain at least 1-5. If you want to translate this language at least 1-5, it means that either there should be 1-5 only, or 2 5s, or 3 5s. These are the only possibilities, yes? So with 1-5, yes? I don't know, let me write it a little bit properly. So with 1-5, how can I calculate this? So the number of numbers with 1-5. Okay, so yes?
You can count with 5 on the left, 5 in the middle, and 5.
So you see that I have to consider a lot of options, yes? So if I consider them, even if I want to count the number of 3-digit numbers with exactly 1-5. By the way, here when I say 1-5, I mean exactly 1-5. exactly 1 5, yes? Okay, so then you say that, okay, exactly 1 5 itself means 3 possible scenarios, yes? Okay, but, okay, so it means that I can consider 3 cases, yes? Either I put 5 here, so all of them, let me write a stage 1, stage 2, stage 3. I put 5 here, or I put 5 here, or I put 5 here, yes? Okay, so assume that I put 5 here. How many options are left for S2? 5 is being dropped. Yes, I cannot use 5 anymore. In total, how many digits I have? I have 10 digits. 5 cannot be used anymore. So how many digits are left? 9. And then how many after that? 9 again. So this is 81. Because it hasn't mentioned repetition is not allowed. It means the repetition is allowed, but 5 cannot be repeated. Yes? Now assume that I choose 5 to be here. Okay? How many options are for choosing the leftmost digit? Yes? 8. Because I cannot use 5. I'm not allowed to use it more than once in this category. And then I am not allowed to use 0. So I am left with 8 options. But then after these are done, how many options are left for this one? 9 again, because the only restriction is that one, so it becomes 72. And I think you agree with me, the next one is also 72, yes? Because then again, I start with this one, 8 options, and 9, 72. So I add them up. So if I add them, by the way, can I add them? Yes, because there is no overlap. If I start with 5, it's definitely different if 5 is in the middle, and it's differently if 5 is the rightmost digit. So there is no overlap. So if I ask you how many of them contains exactly 1 5, you can answer that. So by adding them up, which is 144, it's 225, yes?
Yes.
Okay, this is these items. And then of course, with exactly 2 5s, yes? With exactly 2 5s, something like this. And then, okay, again, how many scenarios I have to consider if I want to have 2 5s? These 2 5s can be against 3 cases, yes? I hope that you agree, it's not that complicated. But it becomes, by the way, complicated if the number of digits is more than that. Because you can say that I can start with a 5 here and there, or I can start with a 5 here and here, or I can have a 5 here and here. Yes? Okay, then it becomes clear. Do you agree with me? If I want to have 2 5s, these are only possibilities for me to arrange 2 5s in 3 spots. Yes? So if I put 5 here and 5 there with exactly 2 5s, so how many options are left for me here? Yes, how many? 9, because I cannot use, this is just multiplication, it's 9. But if I put a 5 here and there, how many options are available for me? 9 again. And if I put 5 here and there, how many options? 8. And then I add them up. It becomes how much? 18, 26. Okay? And then of course the other one is extremely easy to know. I want to have exactly 3 5s. And that is only 555. So with exactly 3 5s, 3 5s, it's equal to 1 item, yes? And that is 555 if you want to write the number. Okay, so the total question mark is 225 of them here, plus 26 plus 1, which becomes what? 252, yes? So this is 252. So you see that I can solve the problem without even using the complement rule. But the complement rule will help you a lot here in this problem by nature of it, yes? So, but I want you to understand how to correctly use the complement rule. So you shouldn't be in a hurry. So you need to know, you should have a good interpretation. So if I consider all 3-digit numbers put in this rectangle, all 3-digit numbers. By the way, if I ask you, do you know the number of items in this rectangle? What is that? 900, yes? So we know the total number. If you don't know, you can calculate, yes? So I would say that the total number of items is 9, 10, 10. It is exactly 900, because the only exception here is that I cannot use 0. Or even though it's so famous, so you know that there are 900 3-digit numbers. But again, I can partition these into 4 pieces, yes? Without 5, with 1 5, with 2 5s, and with 3 5s. Do you agree? So this is the all possibilities. Either the number that you choose does not have any 5s at all, or it contains exactly 1. I mean exactly. I'm a little bit sloppy. Exactly 1 5, exactly 2 5s, and exactly 3 5s. But when you say at least, it means that which parts you are interested in. You are interested in all these parts. This is your question mark. And this is why using the principle directly takes time, because you have to consider 3 parts and add them up. But now you see that what is the complement? The complement of the question mark is just 1 part. Yes? So if I can calculate the number of items here and subtract it from the total number of possibilities, then hopefully I am done. So you see, whenever so when complement rule is useful, when you want to answer a question mark, but if you want to do it directly, you have to consider more cases than the complement case. Yes, here I have 3 separate cases, but the complement is only 1 case. So it is beneficial to think about the complement rule and ask myself, how many items are here? But what is the item? What are the items here? The items that are 3-digit numbers, but without any 5s at all. And this is easy to count. So it means that how many digits are available for me in the first place? 9 digits are available because there are no 5s. And then there is a 3-digit number. 5 is not available for me. How many options I have here? 8, because 5 is not available, but I know that 0 is not possible to put here. It's 8. And then when I go here and there, how many options are left? 9 and 9, yes? So this is 9 and this is 9. And if I multiply them, how much is that?
648.
What?
648.
648.
Yes.
This is the total number here if I multiply them. But my question mark is the total number minus 648. Is that the right number? Yes, so it is 252. And I hope that you agree that this is more beneficial if the number of items are more in the direct calculation. Yes? So this is a good example. I think it's simple, but it shows you how to use the complement rule effectively. Of course, if you write that in the exam, that's also totally acceptable. But I just want you to understand. This method, you see, in this method, I can immediately increase the number of digits. But if I increase the number of digits, say for example, how many 10-digit numbers are there without having, no, but 10 digits is too much. It's 9 digits or 8 digits, but without we'd have at least 1 5. If you want to go in that way, the number of options to do it directly increases. But this doesn't change at all. Yes? Because still your question mark is covering whole parts and the other part. And the only thing that can happen is that the number of stages increases. But that is easy to manipulate. Yes? Okay, so I hope that you understand what is going on. And let me also solve number 3 and then we stop. So how many 3-digit numbers are there so that each contains a digit less than 6? And how many of them do contain exactly 1 digit less than 6? Okay, so let us try to solve that problem. So, how many three-digit numbers are there so that each contains a digit less than 6? So, if you don't mind, let me write all the digits here. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. These are the digits that I can use. How many three-digit number are there that contains a digit less than 6? If you want to solve this problem directly, when I say contains a digit less than 6, how do you interpret that?
Would it be the numbers 1, 2, 3, 4, and 5?
Okay, so in total, if you want to solve the problem, how do you break up the problem? Break down the problem. So I want to have a 3-digit number, and I want to have that contains a digit less than 6. How many of them do contain exactly 1 digit less than 6? So in the first one, I want you to have at least. So might be I should have mentioned that, but I didn't mention that because you need to interpret exactly the words there. So each contains a digit less than 6. So for example, if I write 2, 8, 9, do you accept that this is one of the acceptable items because it contains a digit less than 6? Yes? So if I write this one, what do you think? Is it also acceptable? That's also contain a digit less than 6. Of course, it contains more digits less than 6. Anyway, so in the first one, if you want, I can add the word at least, okay? Contains at least a digit less than 6. So how we can calculate this? If you want to calculate it directly, I think you realize that we have to consider different cases, yes, or at least, yeah. But can we use the complement rule to solve it easier? Mm-hmm.
You can count like so the total and the number, and then those without 6.
And those without 6. And then what is left is at least 1 6. Yeah, so that is what we can do. So the total number is how many? 900. And without 6 is the same problem essentially, yes? So what's the problem here? So I would say that here I have 9 options, and then here I have, I have 8 options, here 9 and 9, yes? And if you multiply that, what is the number? Minus
648.
648. Yes. And then that's the same number, by the way, yes? I don't know why I have written it 2 times, okay? Okay, how many of them do contain exactly 1 digit less? Oh, okay, sorry. This is less than 6. That's not so yeah. This is, I was surprised why I repeated the problem. So this is, I counted the number of them that they don't contain 6 at all, yes? But this is not the 6. Any digit less than 6 is acceptable, okay? So then, yes?
So without any number less than 6. So all of them above. You can
This is correct, yes? So if you want to count the number of them containing at least one digit less than 6, you ask yourself how many of them does not contain any digits less than 6. Yes? So this means that in total, the total number is what? The total number is equal to 900. We calculated sometime. But now we want to see how many of them does not contain any digit less than 6. Yes? So this means that these digits now are forbidden. Okay? So you see it is extremely easier to think in the complement way. Yes? So the total number of, the number of numbers, 3-digit numbers without any digit less than 6. So what is this one? So this means that again I have a 3-stage task to be done. I want to write a 3-digit number, but without any digits less than 6. So they are not available for me anymore. Yes? And then I want to write how many of them are here. I can use any one of them, any number of times that I want to. Yes? So 1, 2, 3, 4. And then how many of them are here? Again 4 and then 4. Yes? So this becomes 64. And then I subtract them. And then the answer is something, yes, 836. I really recommend you go home if you want to practice and understand things in combinatorics very well. Try to solve this problem in a direct way as well. And then you have to come up with this answer. But hopefully you realize that complement rule is really helping. So I need to consider 2 cases: the total number of ways that I can do the task and the ones that I do not desire. And then yes, did I do it right? Yes. 3-digit numbers without any digits less than 6. Yes. Yes. So it means that 64 of them does not contain any digits less than 6 at all. And then when I take them, what is left, it means that there is at least 1 digit less than 6. Okay. Okay, now how many of them do contain exactly 1 digit less than 6? Might be complement rule is not useful for the second one, I don't know. But we want to calculate how many of them do contain exactly 1 digit less than 6. So how should I do that?
like to the left, is less than 6 in the middle.
No, because we also have another freedom, which one to choose. Yes, when I say exactly 1 digit less than 6, I still have some degrees of freedom here as well, because exactly 1 digit less than 6 means exactly 1 5 or exactly 1 4 or up to exactly 1 0. Yes.
You have no digit less than 6.
No, but it doesn't help because I want to have exactly 1 digit less than 5, less than 6. So how should I divide the problem, but into minimum number of divisions?
If the left one is less than 6, then the one is less than 6 and the right one is
Are you sure? So may you repeat it again? Louder?
if, for example, if you count how many are on the left ones, less than 6, the middle one, and then the right one, and then you add.
But are you sure that these are distinct? There is no overlap between them. So let us see what you say. Let us at least, if we cannot solve that. But this is not time. I will probably solve this next time. But what you are saying is that I want to write a 3-digit number. So you consider 3 scenarios, yes? So one scenario is to?
You count the left one, less than 6.
Okay, but less than 6, also 0 is included. Should I don't care about it or should I care about it? Okay, we have to take it into account as well, yes, somehow. But do you want to make it into more branches, considering 0, 1 item, and then not considering 0? So that's what I'm saying. You need to, these problems, you need to sit down and think, and then find the answer. I would recommend you to think about this problem. I will start with this problem next time, okay? Yeah. Yeah, so to see if the complement rule is actually helpful here as well, or we have to do it in the direct way. Okay, so this is your task for the next time, and then I will start with this one and continue. Finally, we start with the things in the book. Any questions? These are all needed in this, but they haven't addressed them so much in the book. There are many things that you need to know. Everything is in the book, but they have rushed over it. Okay, so you need to know about these things. Thank you.